Good morning again. So today we will be starting with the next topic. Herein we will be discussing about the different transforms in brief. Okay. Mainly we will be talking about this Fourier series, Fourier transform. Fourier transform initially. Then from there we will be talking about discrete time Fourier series, discrete time Fourier transform, discrete Fourier transform, and then briefly again we will be discussing about Laplace transform and Z transform. So among all these transforms, you will find that Fourier series and Fourier transform, they are made for continuous time signals and systems. Okay, and these two transforms, the Fourier series and the Fourier transform, they have been used in many areas, including medicine, geology, physics, then electronics and communication, electronics and instrumentation, and so on. The list goes on, and also the electrical engineering, right? So, in all of these things, you will be finding, yeah, again, mechanical engineering also. Mechanical engineering. So you will be finding a wide application of the Fourier series and the Fourier transform. However, they are, as I already told you, they are mainly restricted to continuous time signals and systems. Then comes the discrete time, what you call transforms. Among the discrete time transforms, we have discrete time Fourier series, we have discrete time Fourier transform, then we have discrete Fourier transform. All of these three transforms, they are capable of handling discrete time signals and systems. Okay. However, there are some advantages and disadvantages of discrete time Fourier series and discrete time Fourier transform, due to which we needed a third transform, discrete Fourier transform. Okay. Now, whatever the processing we do in the computer, say if you want to find out the Fourier transform, we basically implement the discrete Fourier transform. Okay. Then then it comes the Laplace transform. This Laplace transform, it is basically again a continuous time transform. I mean to say that it is used for the analysis of the continuous time signals and systems, and it is the generalized version of the Fourier transform. Okay, so from the Fourier transform, if we generalize the equation, we get Laplace transform. However, uh, most of the systems, analog system, what we see, they are being designed in the Laplace transform because of its versatility. Okay. However, why, if we want to design this digital systems, we need to do the same in the Z transform, using the Z transform. Okay, and from the Laplace transform, the Z transform has been derived, which is for the digital or the discrete systems. Okay. However, if you see, since we have derived the Z transform by certain assumptions from the Laplace transform, whatever the system designing criteria which remains for the this analog or the continuous time systems, they are also applicable for the designing of the digital systems with some modifications. So that we will be discussing how it goes. Okay. So mainly what we will be discussing in details is the discrete time Fourier transform. In details, we will be taking up the numericals and all other things, and also we will be looking with the Z transform. Okay. So, however, the understanding of the other transforms is important because without the understanding of the other transforms, you will not be able to understand what the discrete Fourier transform says, or what we want to do with the Z transform, and why it is important in designing the digital systems. Okay, so we will be talking about the 5 and 7 number transforms in details, and all other transforms we will be discussing in short. Okay. Now first comes the Fourier series. So what the Fourier series says. So before getting into the Fourier series, let us discuss about the periodic signals. What we discussed previously is that a signal is periodic if for some positive value of t, this equation it is satisfied, wherein we have xt equals to x of t plus capital T for all t. Okay, that as per the literature, the two basic periodic signals, they include the sinusoidal signal in itself. That means we have the cos omega naught t or sine of omega naught t. Okay, so these two signals are the basic periodic signals because they are sinusoidal in nature. Then we have complex exponential, which is given by xt equals to e to the power j omega naught t. Okay. Now why this is a periodic signal? If you look into this equation, it is nothing but it is in the form of e to the power j theta, which is equals to cos theta plus j sin theta, right? So if you see, it is basically a complex signal wherein we have the sinusoidal signals which we have previously described. Okay, so this herein we have a complex addition of the sinusoidal signals. Okay, and the addition of these two, it results in the complex exponential signals. Okay, so the two basic periodic signals, they include the sinusoidal signal and the complex exponential signal. In both of these equations, if you see, we have omega naught. What is omega naught? Omega naught is nothing but the fundamental frequency. Okay, and from this fundamental frequency, we can calculate the fundamental period where capital T is given by the is regarded as the fundamental period, and this is equal to 2 pi by omega naught. So what is this T? T is nothing but, if you look into our first line, it is some positive value of T. So at what is this T? We just discussed that fundamental period. That means when if you look into this equation, from here we can say that xt is equal to x of t plus t. That means if the signal xt, it is delayed by a fraction of t or advanced by a fraction of t, then it is called and if you get the same signal component, then it is called the periodic signal. Okay, so what is the literal meaning? Literal meaning is that suppose I have got the sinusoidal signal like this. So this is a general term. what I have said previously, that this can be written as t minus of minus t, where this plus means it is being advanced. Okay, so t plus t means we will be moving on the left hand side, and if capital T is negative, it will become this positive will become negative. Okay, so in other words, if you see, if it becomes the positive over here, then we will be having a delay. That means our origin will move on the right hand side. Okay, so on the left hand side we have advance, and on the right hand side we have the delay. Okay, now so if it is t of plus t, that means if you see t of minus t over here, t of minus t, then this origin it shifts to left hand side. Now when it is being shifted to left hand side, if you see, the signal continues. So that even if we delay it by t units, again you will find, if this is the new origin, again you will find that the nature of the signal it remains the same, and this is what it is being shown over here by this equation, where it says xt equals to x of t plus t for all t. Okay, so under this condition our signal becomes the periodic stuff. And as we said, there are two important parameters. One is the fundamental frequency, that is the frequency frequency which is related to the fundamental period, which after which period the signal repeats itself. Okay, so from here, if we come to the what you call this Fourier series discussion, in the Fourier series discussion we have a linear combination of harmonically related complex exponentials of the form this thing xt equals to summation of k equals to minus infinity to infinity ak e to the power j k omega naught t. Okay, so what does this say? This says, if you see over here, we have a complex exponential e to the power in the form of e to the power j theta, which is basically e to the power j k omega naught t. Okay, now what we have seen? We have seen that this complex exponential is nothing but a periodic signal. So what does this equation say to us? This equation say that any periodic signal, it is a combination of various complex exponential signals, that is they are a combination of various periodic signals. Okay, and we have seen that this component e to the power j k omega naught t, it is basically an addition of sinusoids and their real sinusoids and complex sinusoids. Okay, so herein what is k? K are the harmonic components. When k is equal to 0, our ak it becomes constant. So this ak value it becomes a constant which is independent of the frequency. However, when we go on increasing the value of k, k plus minus 1, k plus minus 2, we are basically talking about the harmonic components of the periodic signal. Okay, now when we solve this, if we will come to this equation. Okay, now if you see, what does the Fourier series says over here? The Fourier series says there's xt, it is basically an addition of a naught and some sinusoids. Okay, So that means Fourier series is trying to say us that if there are any signals which are periodic in nature, they can be synthesized using a series of sinusoidal signals. And what does this A0 say? A0 says that suppose there is a DC shaped, let us take this example, this sinusoids. Okay, so for this sinusoid, we can see it is a sine wave signal. Okay, sine wave signal. Now, if somehow this sinusoid it is having a DC shift at a particular level, say over here, and now our signal would be looking something like this, right? Now, under this condition, you can represent the above signal using either cos or sine component. Definitely yes. However, how will you describe this or how will you take into account this shift in this baseline? Okay, from 0 0 it has now come to say a 1 volt component, right? Now how do you govern this one? This one is governed by this A0 component. Am I clear? Now once we have done this, we have seen that Fourier series says that any periodic signal, it is composed of a series of sinusoidal signals. One of the classical example over here is square pulse periodic signal, which is basically a periodic signal. So if you see, we are having some pulses and then we are having the thing. Now if you see, if you add one sinusoid, it is this sinusoid, it is not representing, if you forget this square pulse over here, under no circumstance we will be able to predict that this sinusoid is being used to predict or to reconstruct the square pulse, right? Now when we go on increasing the number of the sinusoids which are being used to reconstruct the square pulse signal, if you see, we are able to get some understanding that what type of signal we are trying to recreate. And when the number of the sinusoids which are being used for the recreation of the pulse, square pulse signals, it is sufficiently high, then if you see, we are able to definitely say, I am talking about this E component, where the number of the sinusoids which have been added at different various sinusoids have been added, and we can see that it is merely estimating the square pulse. However, if you see, there are some deviations in the flat regions, and these deviations, they are called ripples. Okay, and at the discontinuities, you will find there are some large deviations, and these are called Gibbs phenomenon. Okay, so why this Gibbs phenomena occur? This Gibbs phenomena, it occurs because if you look into the original signal component over here, we are saying that infinite number of sinusoids are being used for the recreation of the signals, okay, periodic signals. However, when we are manually doing it, it becomes practically impossible to use infinite number of sinusoids. What we do instead? We use, say, maybe 65 numbers of sinusoids, or 100 number of sinusoids, or 150 numbers of sinusoids, right? So under no circumstances we are able to handle infinite number of sinusoids, and since we are not capable enough to handle such a large number of the sinusoidal signals for the recreation of the periodic signals, this Gibbs phenomena it appears. Not only this Gibbs phenomena but also the ripples what we are seeing over here, right? So this is the thing. However, from here we get an estimate that any square pulse periodic signals, they can be recreated using a series of sinusoidal signals that have different phases and different amplitudes. Okay. Similarly, this is a sawtooth wave. Over here also, we can see different sinusoids are being used, and you can also see the role of phase spectrum. Okay, so as the phase of these sinusoids are being changed, we have talked about the fundamental frequency, right? That fundamental frequency, then we have the harmonic frequencies, they are there. But even in the harmonic frequencies, the phase may be changed, and this change in the phases, they are important in creating any special kind of signals. Okay. Now coming to the Fourier transform. So can anyone tell what is the difference between Fourier series and Fourier transform? What is the difference between Fourier series and Fourier transform? No one? Hello? Can you guys hear me?
Yes, sir.
What is the difference between Fourier series and Fourier transform?
Yes, sir.
No one? Okay.
Yes.
Let's proceed then. So in the Fourier series, we have discussed that we can analyze periodic signals. Right? In Fourier transform, what happens? Can we use periodic signals or can we use aperiodic signals too? Or the other way round, or both of them? The thing is that there is a misconception in many students that Fourier transform, it is used only for aperiodic signals. Okay, and this misconception I have found that it is there in most of the students. Okay, but the answer is that the Fourier transform, it is useful not only for the aperiodic signals but also for the periodic signal. Okay. Now why this is so? I will tell you. If you look into the first assumption of the Fourier transform, in whatever book you take up, you will find the first assumption is a non-periodic signal may be assumed. So this is the assumed assumption that any non-periodic signal may be assumed as the limiting case of a periodic signal where the period of the signal approaches infinity. Okay. So what we have said just before, we have said that if there is a signal xt, periodic signal xt, we can tell it as periodic if it is represented by small t by capital T, where t is finite. Now, in this case, what we are saying, suppose there is some signal like this. There is some signal like this. It goes up to infinity, and then again it starts over here, then it goes and it's, so if you see, again it is infinity. So if you see what this assumption says, this portion of the signal, it is aperiodic in nature. This is aperiodic in nature, right? Now it says at time capital T tending to infinity, it is considered to be a periodic signal. Okay, so we are assuming that a non-periodic signal, it is periodic where capital T tends to infinity. Now if you consider a sinusoid, if it is what do you call, if it is periodic within a finite time, it is also, it is suppose over here it is having the finite time, it is periodic over here. At time tending to infinity also, you will find that this signal is periodic in nature, because for all, we have used a term for all values of t. So you can see, we are considering that the aperiodic signal, they are basically periodic in nature with fundamental time period tending to infinity. And if a signal is periodic within a small time, it will also be a periodic signal up to even when the capital T is being considered to be infinity. Okay, so that's why you will find that the Fourier transform, it is being used to analyze both periodic and aperiodic signals. Now if you see over here, we have started with the equation of the Fourier series, and then after the generalization and all these things, we come to this Fourier transform and inverse Fourier transform equation. Okay, so what it says, if we apply Fourier transform onto a given time domain signal, we can get the frequency domain information, and if we apply the inverse Fourier transform onto the frequency domain signal, we will get back to the time domain signal. Okay, so these two equations you need to remember. Now this figure, it shows us what is basically happening. Suppose we are having a signal ft, and then we apply Fourier transform over here. So over here we are basically applying the Fourier transform equation. Okay, so we get to Fw, which is the frequency domain component. So over here we have applied Fourier transform, and again on this frequency domain signal, if we apply the inverse Fourier transform, we get back to the signal ft. Okay, now why this is important? Suppose there is a saying that if you want to defeat your enemy, you need to understand the characteristics of the enemy in a detailed manner. Okay, in a very minute, you need to have very minute details of your enemy, right? Now, in this case, how does Fourier transform help us? Fourier transform help us. Suppose I give you a signal, say anything. Let us take a what do you call, a square pulse itself. It goes on. So it is basically time and amplitude over here. And then when we apply Fourier transform over here, we get to a position where we get to another domain where we have omega versus amplitude. What is the omega? Frequency. In the first case, what we had amplitude versus time, and in the second case, we had amplitude versus frequency. Now, over here, we will be finding that there are certain peaks. The first one is the fundamental frequency component, and the subsequent ones, they are the harmonics. Now, suppose this signal is corrupted with power line interference, okay, which is either 50 hertz or 60 hertz depending upon the region of the world you are living in, right? Now, if this happens, if your signal is corrupted with 50 hertz or 60 hertz noise signal, they will be overriding the noise component, but you do not have the information from the time domain. Okay, so what type of frequency it is, whether it is a white noise, whether it is a periodic noise, you don't have the knowledge. Even if it is a periodic noise, you don't know at what frequency it is. So how will you design a filter? So here in the Fourier transform, it helps us if we have any power line interference, in addition to the whatever the frequency components we have discussed, we have shown over here, we may be getting a peak around that frequency component. Okay, so from there we will be having an understanding about the nature of the noise. Okay, so once you have once you know the nature of the noise, you can design your filters efficiently. Okay, now you have designed the filters works in the frequency domain. Now you are in this domain. Now again from here, after filtering, you want to go back to the original signal, time domain signal. You apply the inverse Fourier transform and you get the denoise signal. Right? So this is how the Fourier transform it helps. So I have shown you an example using the periodic signal. It is also true for the aperiodic signals. Okay. Again, first one is a non-periodic signal xt, and second one is the periodic signal formed by periodic extension of xt. Now this is a very good chart, and I love this chart. And this chart it gives us a lot of information. We have talked about the LTI systems, and we have talked that LTI systems, they are used in biomedical signal processing a lot. Okay. What is a system? We have already discussed. In a system, we will be having an input xt and we will be getting an output yt. Okay. Now, if this xt, it is an impulse input, that means delta t. That means at time 0, we have an input signal and then there is no signal output. Okay. So if we have this delta t, in yt we will be getting some output. What would be that output? That output is impulse response, which is given by ht. Okay. For input impulse delta t, we will be having an impulse response ht. Now this ht, it is basically providing information about the nature of the LTI system. Okay. The knowledge of this information is very important. Why so? Because This ht, it is basically, as I told you, it is the characteristics of the LTI system ht. Okay. Now if we give a signal input xt, and for that if we know the ht, then yt is given by xt convolution of h of t. Okay, yt is equal to xt convolution of h of t. Okay, now doing the convolution in the time domain, it is bit uh, complex, or it is quite lengthier. So there is another way to do the thing. So what is that? Suppose we have the xt, we calculate x of omega. How we will be calculating? X of omega is calculated by Fourier transform. LTI system, I told you that its property is given by ht. So if you perform Fourier transform of this one, you will be getting h of omega. Then your y of omega, it is nothing but x of omega multiplied by h of omega. Okay. So what are these? This is nothing but your output in the frequency domain. From here, if you do inverse Fourier transform of y of omega, then we get the output yt. Okay. Now if you see the convolution in the time domain, when we have the convolution in the time domain, it becomes multiplication in the frequency domain, and vice versa, So convolution in the time domain becomes multiplication in the frequency domain, and if there is any convolution in the frequency domain, then it would become multiplication in the time domain. Okay. So this is how we can look over here. Okay. So is it clear to all of you? Okay.
Yes, sir.
Yes, sir.
Now coming to the Fourier analysis of the discrete time signals. In the Fourier analysis of the discrete time signals, the main thing is that, as the name suggests, it is a discrete time. It is for the discrete time signals, where signal is represented by x of n, and it is periodic in nature with a period of n. Okay. The same thing what we have discussed with the continuous time. The only thing is that the time domain information, it has changed, where capital N, it is the fundamental period, which is basically the smallest positive integer, and we have a fundamental frequency omega naught equals to 2 pi by capital N. Okay. And during our signals and systems, we have discussed that this omega naught n, this n value, this should be an integer. This n should be the integer, and only then you will be getting that n is an integer, and if n is an integer, then we are having a periodic signal. Okay. Now again, if you look over here, this is our synthesis equation, xn equal to summation of k within the period n, ak e to the power j omega naught n. So again, this is a complex exponential signal, a discrete time complex exponential signal, and from here we can again say that this Fourier series, the discrete time Fourier series, it can analyze periodic discrete time signals in a proper way by synthesizing those signals using a series of sinusoids. Okay. Similarly, we have discrete time Fourier transform. In the discrete time Fourier transform, if you see, this is the discrete time Fourier transform, and where we are getting to the frequency domain from the time domain over here. Okay. Now, if you see herein, we are having summation. Okay, and summation, it can be done for the discrete components. Okay, for the discrete components. On the other hand, if you look into the inverse discrete time Fourier transform, we are having integrals. Okay, now this integration means we are talking about the continuous time domain. Okay, so that means when we are talking about discrete time, discrete time Fourier transform, though the time, it is a discrete component, when we get into the frequency domain, the frequency domain is continuous. Now here is the problem. Now if you have this continuous time domain, the continuous signals, then we have to implement the integral, and if that is so, we have to integrate infinite number of components, and this is what a digital system cannot do. Digital systems can only handle finite number of signal components. Okay, finite number of signal components. So this is the problem with the discrete time Fourier transform. Accordingly, if you see, we had to develop another type of transform, discrete Fourier transform, which can handle or we can generate signals which are having which are discrete in both time domain and the frequency domain, and that would make those systems uh, capable to be handled by the digital systems. Okay. Now coming back to the discrete time Fourier transform, just like Fourier transform, we have a similar analogy. The systems over here, they are LTI systems. Okay. Again, if you give delta n, you will be getting Hn. Delta n is impulse input and Hn is impulse response. Okay. Now this Hn is basically the characteristics of the LTI system. Now if you have Xn, you give it to the Hn and you get the output Yn equals to Xn convolution of Hn. And again you can go for this one, discrete time Fourier transform, you get to the discrete frequency domain. Then from here also you will be getting the h of omega. Okay, and finally you will get y of omega equals to x of omega multiplied by h of omega, and then if you perform inverse discrete time Fourier transform, then you will be getting the yn. Okay. So with this, I will stop today, because I will not start discrete Fourier transform today, because it is a bit long topic, and I want to take a full lecture on this one, so that you have a clear understanding of what we are doing with the discrete Fourier transform. If you have any other questions, I will be happy to answer those. No question?